Welcome to Calculus. Today, we are going to learn a magical mathematical technique called differentiation under the integral sign. If you have ever felt stuck trying to solve a seemingly impossible integral, this is the tool you need. Famously championed by the brilliant physicist Richard Feynman, this method allows us to bypass traditional integration roadblocks by bringing a derivative inside the integral. It is a beautiful, powerful trick that will completely change how you look at complex calculus problems. Let us dive in and see how it works. Now that we know what this topic is called, let us understand why it is so useful. Imagine you are baking a cake. The final fluffiness depends on the oven temperature. Instead of baking many cakes at different temperatures to see the difference, you could just analyze how a slight temperature change affects the chemical reactions in real time. That is what this technique does. We introduce an extra variable called a parameter and take the derivative of the entire integral with respect to it. By swapping the order of operations, differentiating the inside function first, we often cancel out the most problematic parts of the equation. It turns a massive roadblock into a very easy problem. This concept leads us directly to the master equation governing the process, known as the combined Leibniz rule. Conceptually, this formula calculates the total rate of change of an area where both the curve itself and the boundaries are moving. Let us break down the symbols. Alpha is our parameter, the dial we are turning. X is the dummy variable that disappears after integration. The functions a of alpha and b of alpha are the moving lower and upper limits. The formula states that the total change has three parts. The integral of the partial derivative, which measures how the inside function changes, plus two boundary terms that measure how the expanding or shrinking limits affect the total area. If alpha increases, the boundaries might stretch, adding more area, while the curve itself shifts. Having seen the master formula, you might be wondering if we always have to calculate those complicated boundary terms. Fortunately, the answer is no. In most practical physics and statistics problems, the limits of integration are just fixed numbers, like 0 and infinity. Because these boundaries are locked firmly in place, they do not change when we adjust our parameter alpha. Mathematically, the derivative of a constant is exactly 0. This means those two messy boundary terms at the end of the combined Leibniz rule completely vanish. What we are left with is a beautifully simple, highly practical version of the rule that lets us focus entirely on the function trapped inside the integral. This simplification brings us to the most commonly used version of the formula, the constant limits Leibniz rule. Conceptually, because the walls of our area are fixed, the only thing changing is the height of the curve itself. Here, a and b are strictly constant numbers. The partial derivative symbol tells us to differentiate the inner function with respect to alpha, while treating x as if it were just a constant number. This formula is the heart of Feynman's trick. It explicitly gives us permission to slide the derivative operator directly inside the integral sign. If you increase alpha, the function f changes, and this formula captures exactly how that alters the total accumulated area, bypassing the need to integrate the original difficult function. Before we move on, let us see the simplified formula in action with a concrete example. We are asked to evaluate a notoriously difficult integral containing a natural logarithm in the denominator from 0 to 1. Standard techniques will fail here. So, we define the integral as a function of alpha, calling it I of alpha. We choose alpha as our parameter and apply the constant limits Leibniz rule, sliding the derivative inside. Now, we differentiate the inside fraction with respect to alpha. The derivative of x to the power of alpha is x to the power of alpha times natural log of x. Notice the magic here. The natural log of x in the numerator perfectly cancels the problematic one in the denominator. Continuing with our simplified expression, we are left with the integral of x to the power of alpha. This is now one of the easiest integrals in basic calculus. We apply the standard power rule for integration with respect to x. We add exactly 1 to the exponent, making it alpha plus 1, and divide by that new exponent. Next, we evaluate this across our boundaries from 0 to 1. Plugging in the upper limit of 1, 1 raised to any power is just 1. Plugging in the lower limit of 0 gives 0. So the entire definite integral collapses down to a simple algebraic fraction, 1 over alpha plus 1. We have successfully found the derivative of our integral. To finish this problem, we must remember our goal is to find the original integral I of alpha, not its derivative. So, we integrate our result, 1 over alpha plus 1, with respect to alpha. This gives us the natural logarithm of alpha plus 1 plus an unknown constant of integration c. To find c, we look back at our original integral and pick a clever baseline. If we set alpha to 0, the numerator becomes 1 minus 1, which is 0. So I of 0 must be 0. Plugging this into our logarithmic equation, we find that c equals 0. Our final answer is simply the natural log of alpha plus 1. A physically impossible-looking problem solved elegantly. Let us tackle another famous problem, often used to showcase Feynman's trick. We are given an improper integral from 0 to infinity with an annoying x in the denominator. We will treat b as our parameter and define the integral as I of b. We apply Leibniz rule, moving the derivative with respect to b inside the integral. When we differentiate the sign of b times x using the chain rule, it pulls out an x. This is exactly what we want. The x in the numerator perfectly aligns with the troublesome x in the denominator, and they cancel each other out entirely. We have removed the singularity that made this integral impossible to solve normally. Continuing our derivation, we are left with the integral of an exponential multiplied by a cosine function. This is a very standard form in physics and engineering, often recognized as the Laplace transform of a cosine function. Instead of doing tedious integration by parts twice, we can use the standard formula directly, which gives us a over a squared plus b squared. Now we have the derivative of our integral. To recover the original integral I of b, we must integrate this new algebraic fraction with respect to our parameter b. This step moves us from the rate of change back to the total accumulated value we are seeking. We now perform the integration with respect to b. The integral of a constant over the sum of squares is a classic inverse trigonometric identity, yielding the inverse tangent or arctangent of b over a plus our constant of integration c. To lock down the exact formula, we need a baseline. Looking at the original integral, if we set the parameter b to 0, the sign term becomes 0, collapsing the entire integral to 0. Substituting I of 0 equals 0 into our arctangent equation, we find that c is exactly 0. We substitute this back to get our final closed form solution. The physical meaning here is profound. An infinite accumulation is perfectly described by a simple angle. Now that we have mastered fixed limits, let us look at a case where the boundaries are moving, requiring the full combined Leibniz rule. We want to find the derivative with respect to x of an integral where x appears inside the function, in the lower limit and in the upper limit. We carefully set up our three terms. First, the integral of the partial derivative of the inside function. Second, we plug the upper limit x squared into the function and multiply by its derivative, 2x. Third, we subtract the lower limit plugged into the function multiplied by its derivative, 1. Inside the integral, differentiating sine of x times t with respect to x pulls out a t, which cancels the denominator. Continuing with our expanded equation, we simplify the algebraic fractions in our boundary terms. Now we are ready to perform the integration of the remaining cosine term with respect to the dummy variable t. The antiderivative of cosine is sine. Because of the constant multiplier x inside the argument, we must divide the result by x. We then evaluate this newly integrated term across its boundaries, substituting the upper limit x squared for t and subtracting the result of substituting the lower limit x for t. The boundary terms we calculated in the previous step simply carry down unchanged to join this new expression. We are almost at the finish line. For our final step, we simply combine all the similar terms together to reach our simplified answer. We have one sine of x cubed term from the integral evaluation and two more from the upper boundary, giving us a total of 3. We have a negative sine of x squared term from the integral and another negative one from the lower boundary, giving us negative 2. This final expression perfectly captures the total rate of change of the complex integral. It successfully accounts for both the changing function inside and the expanding boundaries of the integration area. This demonstrates the full incredible power of the combined Leibniz rule. Let us visualize exactly what we have been calculating. Look at this graph showing a function plotted against the x-axis. The vertical dashed lines at x equals a and x equals b represent our fixed limits of integration. The area between these lines is our integral. Notice the 3 different bell curves. These represent our function at different values of our parameter alpha. As alpha increases from 1 to 3, the curve stretches upwards. The arrow labeled with the partial derivative shows this vertical growth. Differentiation under the integral sign calculates exactly how fast that total shaded area is growing as we turn the alpha dial, without needing to calculate the total area first. We have covered a lot of ground today, so let us review the key takeaways. First, differentiation under the integral sign, or Feynman's trick, is a powerful shortcut that swaps the order of operations to make impossible integrals solvable. Second, by introducing a parameter and taking a partial derivative, we can often cancel out problematic terms, like a pesky denominator. Third, we use the constant limits rule when our boundaries are fixed numbers, and the full combined Leibniz rule when our boundaries are moving. You now have a master-level tool in your calculus toolkit. Excellent work today. You have conquered one of the most elegant tricks in mathematics.